Hello everyone, this is Vasishta from Aerobi section. Today I am going to explain a topic about transient heat conduction from heat mass and transfer. So transient heat conduction consists of a lumped system analysis. In heat transfer analysis, some bodies are essentially isothermal and can be predicted as lump systems. An energy balance of an isothermal solid for the time interval dt can be expressed as heat transfer into the body during dt, that is equal to HAS T alpha minus T infinity minus T dt is equal to MC dt. The increase in the energy of the body during dt, solid body, which is Q is equal to HA into T alpha T infinity minus T. Noting that M is equal to rho V and dt is equal to D into T minus T since T alpha T infinity, which is equation 4, can be rearranged as dt minus T infinity by T minus T infinity is equal to HAS by rho V Cp dt. Integrating from time 0 at which t is equal to ti to t gives ln t minus t infinity by ti minus t infinity is equal to has by rho v cpt. Taking the exponential of both sides and rearranging t into t minus t infinity by ti minus t infinity is equal to e power minus vt. That is equal and that b is equal to has by rho v cp in 1 by s, where b is positive quantity whose dimension is t time power minus 1 and called time constant. There are several observations that can be made from this figure and the relation above. Equation 4 enables us to determine the temperature of a body at a time, or alternatively the time t required for the temperature to reach a specified value. The temperature of a body approaches the ambient temperature T exponentially. The temperature of the body changes rapidly at the beginning but rather slowly later on. At larger value of P indicates the body temperature, body approaches the ambient temperature in a short time. Rate of convection heat transfer. We all know that the convection of a heat transfer is equal to Q is equal to HA into T minus T infinity, where the rate of convection heat transfer between a body and the ambient can be determined from the Newton's law of the total heat transfer between the body and the ambient over the time interval 0 to T is simply change in the energy content of the body, where that is equal to Q is equal to mCp into T into T minus T infinity. Where the maximum heat transfer between the body and its surroundings is that mCp into T I minus T infinity. Criteria for lumped system analysis. Lumped system is not always appropriate. Characteristic length LC is equal to V by AS and a Biot number as BI is equal to HLC by K. It can also be expressed as BI is equal to LC by K by L by H. That is equal to R conduction by R convection. That is equal to conduction resistance within the body by conduction resistance at the surface of the body. Lumped system analysis assumes an uniform temperature distribution throughout the body, which is true only when the thermal resistance of the body is heat conduction is zero. The smaller the BI number, the more accurate the lumped system analysis. It is generally accepted that lumped system analysis is applicable if BI is less than or equal to 0.1. Transient heat conduction in large plane walls, long cylinders, and spheres with spatial effects. Where in many transient heat problems, the Biot number is larger than 0.1 and the lumped system cannot be assumed. In these cases, temperature within the body changes appreciably from point to point as well as within time. It is constructive to first consider the variation of temperature with time and position in one-dimensional problem of rudimentary configurations as large plane wall, a long cylinder, and a sphere. As you can see, this is a large plane, this is a large cylinder, and it is a sphere. The heat conduction equation. We all know that the one-dimensional transient heat conduction equation consists of differential equation which is dou square T by dou x square is equal to 1 by alpha into dou T by dou T, where T is temperature, capital T is temperature, small t is time. Boundary conditions. Dou T by dou x 0 comma T is equal to 0 minus k into dou T by dou x L T, that is equal to h into T L comma T minus T infinity. Initial condition. T of x comma 0 is equal to Ti. Summary of the solution for one-dimensional transient conduction. Summary of the solution for one dimension in the plane with thickness 2L and the radius R and the sphere of radius R not subjected to convection. Here in case of plane wall, cylinder and sphere, these are the solutions that are required for the transient conduction. Here theta is equal to T minus Ti into by T infinity minus Ti. It is the dimensionless temperature. Ba is equal to HL by K or HR not I LK is the Biot number. There is a topic called Heisler chart. The solution of the transient temperature for a large plane or long cylinder and sphere are known presented in a graphical form for tau is greater than 0.2, known as the transient temperature charts, also known as the Heisler charts. There are three charts associated with each geometry. The temperature T0 at the center of geometry at the given time T, the temperature at other location at the same time in the temperature of T0, the total amount of heat transfer up to time T. This is a Heisler plane wall with the midpoint temperature. Heisler charts of a plane wall. The temperature distribution initially T is equal to Ti, T infinity H L X. Transient heat conduction in semi-infinite solids. A semi-infinite solid is an idealized body that has single plane surface and extends to infinity in all directions. Assumptions: constant thermophysical properties, no internal heat generation, uniform thermal conduction on its exposed surface, initially a uniform temperature of Ti throughout, heat transfer in the case occurs only in the direction normal to the surface, the x direction, one-dimensional problem. Transient heat conduction in multi-dimensional systems. Using a super Using a superposition approach called a product solution, the one-dimensional heat conduction solution can also be used to consider solution for some two-dimensional and even three-dimensional transient heat conduction problems, provided that all surfaces of the solid are subject to convection to the same fluid temperature, the same heat transfer coefficient H, and the body involves no heat generation. Total transient heat transfer. The transient heat transfer for two-dimensional geometry form an intersection of two-dimensional to one-dimensional geometry is 1 that is q by q max is equal to q by q max 1 plus q by q max 2 into 1 minus q by q max into 1. Transient heat transfer for a three-dimensional is q by q max is equal to q by q max 1 plus q by q max 2 to 1 minus q by q max 1 plus q by q max 3 into 1 minus q by q max 1 minus q by q max 2. This is all my explanation. Thank you.